let's hijack an airplane without killing the pilot, without killing the terrestrial personnel, without touching the airplane, and without touching the communication system. Airplane is a very wonderful thing, and it's very safe because you will end up on the ground. The question is only where and how. An airport would have been a better choice, but as I can see, the airplane is almost engrossed, so maybe it can fly again, but not now. Flying can be separated to three parts: starting, flying a distance, and landing. Starting is very simple. It's, I would say, the most simplest part of the flight. But flying the distance and finding the target is a bit more sophisticated. There are several methods. For example, the Lorentz system was developed in the 1930s, and it uses long-wave transmitters, and the airplane calculates its own position by the signal strength and the propagation time. So it's exact enough to find the airport, but not exactly enough to finding the touchdown point. One more modern version is the GPS. At present, there are 4 GPS systems on the Earth. GPS and GLONASS is public, so everybody can use it. And Galileo and the Chinese version is in test version, so you can detect the signals, you can use it, but there is no guarantee that it's exact and contains real information. But GPS also not exact enough for an exact landing. When you want to get to the airport, GPS can be sufficient, but if you want to find the touchdown point, you need more than 10-meter accuracy. When the old times, every airplane will get down, so somehow it can be directed to the airport. There were 2 methods. One, when you can see everything, every object on the Earth can be visible, you can visually detect the touchdown point and manage the plane come down. The other ways was when you cannot see anything, and it was very interesting. There was on the Earth a so-called listener who tried to detect the direction of the airplane by the voice of the airplane, and in every 30 seconds they had to send that position to the airplane, and by that information the pilot tried to touch down the plane. So if you can see everything, we can say we fly according to the visual flight rules. If you cannot see anything, the method is instrumental flight rules. Your every action based on the information given by the equipment on the board. The more spreaded method is the ILS, the Instrumental Landing System, developed in 1940 in Minnesota, and it defines a so-called funnel to the airport, to the touchdown point, and that funnel can be detected on the airplane without any external help, and defines the touchdown point with some meter precision. So, when the weather is clear, we don't need the ILS. We can fly according to the visual flight rules. If we cannot see anything, we must use the IF, and we work according to the instrumental flight rules. When can we use it? Both the airport, the airplane, and the pilot together must be qualified for ILS use. What does the ILS do? This is an airport, Budapest Ferihegy, and here is the touchdown point. We have to guide the airplane to the touchdown point in the direction of the runway. So not across the runway, along the runway. And at the same time, we should define the glide slope, how fast can the airplane lower the altitude and the speeds too. The ILS. There are two significant signals. The localizer defines the runway and the direction of how to get there, and the glide slope, the descending rate of the airplane in order to get to the runway at the defined touchdown point. There are two radio signals for defining this funnel, one for the horizontal one for the vertical part. For the horizontal part, we call them localizer signal. Localizer defines how to get into the direction to the runway. The vertical part is the glide slope. How can you decrease the altitude of the plane, the vertical approach of the touchdown point? Both the localizer and the glide slope is radiated with special antenna system, and they radiate steady signals. So there is no change in the radiation. The airplane itself will be able to evaluate its position. This is the funnel. One side of the localizer signal is modulated with 150 Hertz. The other side is with 90 Hertz. The glide slope is about the same, but in a different frequency range. The upper side is modulated with 90 Hertz. The downside is 150 Hertz. The radiation direction depends only on the antennas. So on the terrestrial part, on the ground, there is no change in the radiation. So the airplane itself will be able to define its own position. This is the localizer antenna group and the radiation characteristic of the localizer. So if the airplane is on the right way, on the right heading, the ratio of two frequency signal will be 1:1. If the airplane goes right or left, the ratio will change and it will be easily detected on the board. The glide slope antenna and its radiation characteristics. So if the airplane is on the right glide slope, the ratio of two signals is 1:1. If diverts from the right direction, either the 90 Hertz component, or if it's too low, the 150 Hertz component will be higher, and it will be visible for the pilot, or it will be usable for the autopilot. There is a very simple instrument to detect the signals and visualize it. There is a normal radio receiver, demodulator, audio amplifier, and a headphone for the acoustic verification of the signal. It's not so important because those are steady signals, so you will hear only humming noise. But you can detect that, yes, really I have an ILS signal. And there are two filters, one for the right channel, one for the left channel, or higher channel, lower channel, and a single cross-pointer instrument for visualize where we are. So this is the phonogram and the signals. If the airplane is too low and too far left, this is the picture on the instrument. That means that you should push down the nose of the plane, rise the nose of the plane in order to push down that line, and turn right in order to move that line to the center of the instrument. If the airplane is on course, both the glide slope and the localizer signal will be on the cross. So this is the picture when the airplane is on the right track, and these are the signals radiated by the localizer. When the airplane is left from the right track, that will be visible. Right from the right track, you can see the cross moved on the opposite direction. And when airplane is out of range, so out of the radiation characteristic of the antenna, there will be a warning, there is no navigation. We are out of range, the automatic system cannot find the real position of the airplane. There are different frequencies for the localizer and the glide slope, and any airport you approach will publish its localizer frequency. Localizer frequency will define the pair on the glide slope. Glide slope frequencies are higher because the accuracy of the system depends on the wavelength. That means 300 megahertz band is about 1 meter wavelength. That means the vertical accuracy can be 50 centimeters. The localizer wavelength is about 3 meters. That means the horizontal accuracy can be 1.5 meters. There are different categories depending on the antenna system. And the first category is almost sufficient to find the airport and a slightly foggy time touching down the plane. DH, decision haze. This is the lowest altitude the pilot should decide whether they want to land or restart the flight. 200 feet is about 65 meters, and RVR is runway relative visibility. How long should the pilot see the runway? 2,400 feet is about 800 meters. I would say nowadays there is no Category 1 ILS systems. Category 2 is very popular because 30 meters decision haze and 400 meters horizontal visibility is sufficient for the most non-commercial flights. Commercial flights use category 3A, B, and the autopilot systems category C. In category C, there is no decision height and no any visibility limits, so I would say you only have to pray, and the autopilot will do everything else. In the Die Hard 2, there was something similar screen where the decision haze was negative. And finally, the plane ditches into the ground. So, Budapest Airport, Jeppesen is a special flight map publisher. They give all the necessary information for the approach and touchdown, and they give the localizer frequency. The localizer frequency defines the glide slope frequency too. So you can see, you can approach the airport this way if you come from north. This is the heading of the runway, and this is the localizer frequency. This is the communication with the tower, and so on. So, when can you use the ILS? What is the longest range when you can use? Jeppesen says that in his opinion, it's about 33 kilometers, 18 nautical miles. But the official value is 25 nautical miles. It's about 46 kilometers. So if you want to forge the ILS signal, you have only 35, 45 kilometers in flight, and in time 3 or 4 minutes, depending on the speed of the airplane. If you want to redirect an airplane, you have to forge the ILS signal. ILS signal is not so strong because it's a directed signal, especially for the official direction of the flight, and the antenna gain is very high, so some 100 transmitting power is sufficient for directing the plane in 45 kilometer distance. But it's easy to suppress it because the field strength decreases with the second order of the distance. So for 30 kilometers or 45 kilometers, the official ILS signal is very, very weak. So if you can radiate to another signal to the airplane, direct it to the airplane, or radiate a signal on the board of the airplane, you can suppress the official ILS signal, and your signal will control the airplane. This is the runway and the significant parts of the runway. Threshold is the first place you can touch with the airplane. If you come short, it will be a bit hard. Behind the threshold, there is a signification information for visible approach, the name and the direction of the runway, and here is the touchdown zone. This is the first official point where the airplane should touch the runway. This is the latest point, the aiming point. That means that the airplane should touch down somewhere between the touchdown zone and the aiming point. if you want to simulate or generate an ILS signal, you have to know some informations. For example, the exact coordinates of the target, including the elevation. What does it mean? The elevation is the height of the runway above the sea level. The azimuth, the direction, the heading of the runway, the expected glide slope, how fast can the airplane reduce its altitude, and you should know the actual position of the airplane and the acceptable glide slope. Acceptable glide slope means that, for example, a glider, they can use a higher glide slope than an Antaeus with full load, which will come on a light glide slope. So, this is the actual position of the airplane. This is the touchdown point. That was the aiming point, that when at the touchdown point and this point leaves a free place for the pilot for decreasing the horizontal speed of the airplane. So we know the actual position, the coordinates of the touchdown, the azimuth, the heading of the runway, the expected glide slope, and everything else is only trigonometry. So this is the calculation of the localizer. We know the actual position, we know the target position, and we can calculate which ILS signal we should radiate, 90 Hz or 150 Hz. We know the actual height, we know the end of the runway position, and we can calculate which signal we should radiate for the right glide slope transmission. For the actual position, we need a GPS receiver. This is an old one, an almost military-grade receiver, but we can use only a $5 Chinese receiver, or a USB stick. When we started to work out this method, we worked with this one. We need a laptop with the appropriate program. And I hope I will be lucky to switch between the applications, because okay. Most kéne ez még. Jó, kösz. This is the program. We can choose between the pre-programmed runways, or we can define new runways by giving the coordinates, giving the name, or we can modify any it's a Windows, excuse me. But there is only one more thing I would like to show you. The test mode. Do we have sound?
Igen, ezt ki fogom húzni, és akkor megállni oda került, ott tudja. Ott van neki.
Aha. Tehát tesztmódban megint elszálltunk a Windows-zal. So in test mode we can This is a protected airplane. So in test mode, we can test the ILS system of the airplane. If I push to the right side that signal, I will hear 90 Hertz. On the other side, I will hear 150 Hertz. So this way, if I don't want to hijack a real airplane, but I want to help a pilot with an ILS support on an airport without ILS support, I can check whether my device is working correctly and it's accurate and it's synchron in the onboard system. So we need an ILS transmitter or two transmitters. One for the localizer band, another one for the glide slope. The output power is very, very small. It's about 5 milliwatts. How much is 5 milliwatt? If you have a garage remote control, it's 10 milliwatts output power. So about half of this is sufficient to control the ILS system. We have a so-called ILS selector box. It can be omitted because at the beginning we used it as a hardware component, but this part can be done by the PC. So the whole setup is only some components. This is the screen without the real-time part. I would have liked to show you how can we calibrate the system, but Bill Gates wanted something else. These are the offline screens. And how can we use it, and what is the purpose of this solution? We can use it to substitute the ILS signal on airports without ILS support. So we can educate using of the ILS on airports without ILS. We can support the precision touchdown on airports without ILS support. We can provide emergency transportation for precision touchdown for emergency transformation. So if there is a person on the earth who can tell me the exact coordinates of a safe touchdown point, I can direct the plane to that point. And we can define meeting points anywhere in the air. The dark side is this rig can suppress the ILS signal, it can substitute the original ILS signal, and this way, on the last 45 kilometers, on the last 5 minutes, we can define a new target and we can hijack the airplane. And you cannot touch either the airplane or the navigation system or the staff. You can do it from the passenger compartment. A very sad situation in 2010, the Polish Air Force One ditched into the forest because that airport didn't have ILS support and the plane was flight by radio altimeter. Radio altimeter measures the actual haze of the airplane, but there was here a valley below the level of the airport. So when the altimeter said that you are too low, it was too late. So this sad event could have been prevented with an IL support. Some doubts. We started with a fairly strong laptop, a professional GPS receiver, homemade selector, and 2 transmitters. Now, the program is less than 500 kilobytes. It can run on a netbook, and we can use an inexpensive GPS dongle. And we need the 2 transmitters. I'm pretty sure that tomorrow the program will be able to run on smartphone with the built-in GPS, and will be able to drive 2 simple garage remote controllers. And the whole thing can be easily taken to the airport, because smartphone is a very common thing, remote control is a very common thing, and if you connect them to each other, you can emulate the ILS signal. And now the video. We have done the show.
Flown to airfields with no ground-based radio navigational equipment installed. In these cases, a portable device carried on board generates the data for the localizer and glide slope that are transmitted to the ILS receivers of the airplane using radio signals. The system consists of a couple of simple parts, such as a portable computer, 2 small-sized radio transmitters with antennas, an interface, and a GPS receiver. All these parts use their own batteries, thus there is no need to physically attach it to any of the aircraft systems. The parts can be assembled easily in less than a minute. These tools can be kept in the cockpit, the passenger cabin, or even in the cargo area, since there is only radio connection between the equipment and the instruments of the aircraft. After installing the antennas, you select the runway you intend to use, set the course of the localizer, set the angle of the glide slope, and you are ready for shooting ILS approaches. The GPS receiver in this particular case sends the signal for the portable computer via Bluetooth device. In a well-equipped airplane, like the one we are on board now, automatic approaches can also be practiced. Interception and following the localizers and glide slope is done exactly the same way as if it was at an airfield with ground-based ILS facilities. This time the ILS approach is made to a former military airfield with no navigational aid. The accuracy of the approach is guaranteed by the GPS receiver and the algorithm of the computer. Here you can see a simulated ILS approach to runway 09er at Lima Hotel Bravo Sierra near Budapest, Hungary. Simulated ILS approaches can be set up to any runway at any airport, even those with short grass fields, but you always have to consider obstacle clearance. In case there is no sufficient clearance above the obstacles when you want to build up a 3-degree glide slope for the threshold of a short sport landing strip, it is good practice to displace the virtual touchdown zone to the middle of the runway, thus assuring the safe altitude above the obstacles around the airfield. In these cases, low approaches should be flown without actual landings. Here's another approach to the opposite end of the same runway at Lima Hotel Bravo Sierra to runway 27 from the left-hand traffic pattern. You can set up virtual runways with touchdown zones, localizers, and glide slopes, not only to existing airfields, but anywhere, even up at altitude in a practice area or above the actual traffic pattern of the airfield, thus further simplifying the conditions for uninterrupted practice of ILS approaches. The unprecedented advantage of this system is that you don't need to fly to airports equipped with ground-based ILS to be able to practice equivalent ILS approaches. These kind of airports are usually far from the base airfield of the training organization and are quite busy with commercial traffic. For these reasons, it is not easy to accommodate training flights, or considerable time is wasted on holdings. The other big technical advantage is that this equipment does not need to be connected to the aircraft or any of its systems, thus no need for shop assembly or any official approval. The radio signal is so weak that it can only be received in a range of a couple of yards. solely for the purpose of transmitting the signal to the airplane's own antennas. Therefore, it does not disturb any other aircraft in the air. Using this equipment, the efficiency of training or practicing ILS approaches increases dramatically, regardless of the type of approach, whether it be raw data, flight director, or autopilot approach. ILS approaches are the most complex maneuvers of IFR flying, and as such are the best and most commonly used testing methods when evaluating flying skills.
So that's the mobile ILS station.